All right, get ready, because today we're diving deep into the periodic table.
Ooh, sounds exciting.
It is. We're using an excerpt from, believe it or not, a DAT study guide
Okay, a study guide.
as our roadmap. But trust me, this is way more fascinating than just memorizing elements and their symbols, right?
Oh, absolutely. It's like uncovering this hidden language.
Yeah.
The patterns and the trends that explain, why elements act the way they do.
It's like figuring out their personality.
Exactly.
But to do that, I think we need to start with some basics. So
Okay.
I remember learning about groups and periods, but honestly, it's a bit fuzzy now. Could you remind me what those are?
Yeah. So think of the periodic table as a city with, streets and avenues.
Oh, okay.
And the vertical columns, those are the groups. Elements in the same group share similar chemical traits, like neighbors on the same street. Maybe they have similar lifestyles.
I like that. That makes sense.
Yeah, and the horizontal rows, those are the periods. And as you move across a period, the elements kind of gradually change their properties, like walking down a street and seeing how the houses, slowly change in style.
I can picture that.
Yeah.
So what makes elements in the same group act so much alike?
Well, it all comes down to those outermost electrons in an atom.
Oh, valence electrons, right?
Exactly, valence electrons. And they're the ones that are really responsible for bonding
Right.
and forming relationships, you could say, with other atoms.
They're kind of like the social butterflies
They are.
of the atom.
Yeah, so elements in the same group have the same number of these valence electrons, which is why they kind of behave similarly.
So is that why, like, the alkali metals in group 1 are so reactive?
You got it. They only have one valence electron.
And they're ready to share it.
Yeah, they're eager to bond with other atoms. And then, on the other hand, you have the noble gases in group 18.
Yeah, they're pretty chill.
Yeah, they have a full house of valence electrons,
Mm-hmm.
making them very content and unreactive, like the introverts.
I love these analogies.
Yeah.
Okay, now I remember our source also mentioned something about oxidation states.
All right.
And I remember those being important, but can you remind me what they tell us?
Yeah, so oxidation states are a way of tracking how many electrons an element has gained or lost
Okay.
when it's forming a bond.
So it's like an atom's charge.
Exactly.
Yeah.
It's like their charge or balance in their relationships with other atoms.
Oh, okay, and this is where transition metals get interesting, right?
They do, yeah. So transition metals are those elements in the middle block of the periodic table, and they can have multiple oxidation states.
Multifaceted.
That's a good way to put it. And this is because they have electrons in their orbitals, which can participate in bonding in a bunch of different ways.
So they can adapt to different situations.
Precisely.
Interesting.
Yeah, like take manganese, for example. It's found right in the middle of the transition metals, and it can have oxidation states ranging from +2 all the way to +7.
Wow, that's a lot.
It is. And this makes it really important in a lot of biological processes. Did you know that it's a crucial component of the oxygen evolving complex in photosynthesis?
What?
Yeah.
So it helps us breathe.
It does.
That's amazing.
Yeah.
Now, our source also mentions intertransition metals. Are those just kind of like shy transition metals?
So they're often kind of tucked away at the bottom of the periodic table,
Yeah.
almost like footnotes, but they're far from unimportant. The intertransition metals, the lanthanides and actinides, have their own special properties because their valence electrons are found in orbitals, which behave differently than those d orbitals.
So they've got their own unique talents.
They do.
Very cool.
Yeah, they're just not always in the spotlight.
I see. Now, speaking of elements with unique talents, our source also mentions this mnemonic: have no fear of ice-cold beer.
Oh, yeah, that's a classic.
It's a good one. It helps us remember the 7 elements that exist as diatomic molecules.
Right. Naturally as pairs.
Exactly. Hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine.
Yep. And these elements are so reactive that they're way more stable when they're just paired up with themselves.
Like they can't stand to be alone.
Exactly.
Okay, so why are they so much more reactive than other elements?
Well, it comes down to, their electron configurations and how badly they want to achieve that, stable, full outer shell of electrons.
Okay, so they're kind of desperate to fill that gap.
They are, yeah.
So they readily, share electrons with another atom of the same element.
Exactly.
Okay, I get it.
Yeah.
That makes sense. Now, I also remember learning about, trends in the periodic table.
Yes.
How the size of an atom or its atomic radius changes as you move across or down the table.
Absolutely. That's a very fundamental property.
Yeah.
And it sets the stage for understanding a lot of the other trends.
Okay.
So atomic radius is basically just a measure of an atom size, how much space it occupies.
Right.
And here's where it gets interesting. Atomic radius increases as you move down a group,
Okay.
and from right to left across a period.
So the biggest atoms would be like cesium and francium.
You got it. And the smallest are up at the top right, like fluorine and oxygen.
Got it. Okay, so why does this trend exist?
So imagine the atom's nucleus as like the sun,
Okay,
and the electrons are like planets orbiting around it.
I like that.
As you move down a group, you're adding more electron shells, like adding more planets to the solar system, so that naturally increases the atom's overall size.
Okay, so more shells equals more space.
Yep. More space, bigger atom.
But what about moving across a period?
So that's where the concept of effective nuclear charge.
Oh, Zeph, right.
Yes, Zeph. It comes into play.
Okay, remind me what that is.
So it's a measure of the attractive force that the nucleus exerts on the electrons.
Okay, like the sun's gravity on its planets.
Exactly. So as you move across a period, the number of protons in the nucleus increases.
Right.
Which, would normally increase that attractive force.
Right.
However, the number of electron shells stays the same, so the inner electrons actually shield the outer electrons from the full force of the nucleus.
It's like the inner planets blocking some of the sun's gravity from reaching those outer planets.
Exactly.
I can picture it.
So this shielding effect reduces the effective nuclear charge, that Zeph, experienced by the outermost electrons.
Okay, but the number of protons is still increasing.
Yes. And as you move across the period, that number of protons increases more than the shielding effect can, compensate for. So the overall Zeph still increases.
So the pull from the nucleus is still getting stronger.
And a stronger pull means the electrons are drawn in tighter.
Resulting in a smaller atom.
Exactly.
This is like a cosmic tug of war
It is.
going on.
It really is.
Now, our source also mentions this thing called an isoelectronic series.
Yes.
Is that related to this whole tug of war concept?
It is. An isoelectronic series is a group of atoms and ions that have the same number of electrons, like competitors in the same weight class.
Oh, okay.
And our atomic tug of war.
I like that.
Yeah. So this allows us to kind of isolate the effect of the nuclear charge on the size of that atom or ion.
Okay, so if you have like a series of ions with the same number of electrons, the one with the most protons is going to be the smallest.
You got it. Because its nucleus is pulling those electrons in with the strongest force.
Right, okay.
It's like having a more powerful magnet attracting, the same number of iron filings.
The stronger magnet, the closer they get.
Exactly.
Okay, that makes sense. Now, what about ionization energy? I know it's a big deal, but can you remind me what it actually measures?
Yeah. Ionization energy is the amount of energy it takes to remove an electron from an atom.
So the higher the ionization energy, the harder it is to, pry that electron away.
Exactly.
Okay.
And just like atomic radius, ionization energy follows a trend. It increases from left to right across a period and up a group.
So as you move across a period, the effective nuclear charge increases.
Right.
Which means that nucleus is holding onto those electrons tighter.
Yeah.
So it would take more energy to remove them.
Brilliant. Exactly.
Okay, and as you move up a group, those electrons are closer to the nucleus. So they're also harder to remove.
You got it. So elements in the top right corner of the periodic table, like fluorine and oxygen, would have very high ionization energies.
They do not want to let go of their electrons.
They do not.
Now, are there any exceptions to this trend?
There are. One interesting one is the alkaline earth metals. Those in group 2, they have slightly higher ionization energies.
Really? Why is that? I thought it was all about the pull from the nucleus.
So it is, but there's another factor here. Electron configuration.
Oh, right.
Alkaline earth metals have completely filled orbitals in their valence shell, and this filled orbital configuration provides extra stability.
So it makes them less willing to give up an electron.
Yeah, less willing to react.
Interesting. So it's kind of like if it's already stable, it's not going to react as much.
Exactly. And this brings us to another exception. The group 15 elements.
Oh.
They have a half-filled perorbital, which also confers some stability, and this leads to slightly higher ionization energies than you would predict, just based on where they are on the periodic table.
So electron configuration really does play a role.
It really is.
In how an element behaves.
Yeah.
Fascinating. Now, what about electron affinity?
Oh.
Remember, that has something to do with gaining electrons.
Yes, electron affinity is the energy change that occurs when an atom gains an electron.
So it's like how much an atom wants to, snag an extra electron to complete its outer shell.
Exactly.
And the trend for that is kind of similar to ionization energy.
It is. So generally, Electron affinity follows the same trend as ionization energy.
Increasing across and up.
Got it.
Okay, so again, those elements on the top right of the periodic table, like the halogens, they would have very high electron affinities.
Yes. They have a really strong desire to gain that one extra electron to complete their valence shell and reach that, like, coveted noble gas configuration.
But of course, there are exceptions.
Always.
Always exceptions.
Yeah, so group 2 elements with their filled sorbitals have really low electron affinities.
They're content.
They're happy with what they have, and they're not as eager to add an extra electron.
Makes sense. What about group 15 elements?
So they have those half-filled orbitals.
Right.
We talked about.
To give them that stability.
Exactly. So they're also not as enthusiastic about gaining another electron.
They're good.
They're good.
Right. And noble gases.
They have practically 0 electron affinity.
They're just chilling.
They're in a state of zen.
They have a full valence shell already.
They're happy.
Perfect.
Yeah.
Now, how does electronegativity fit into all of this?
So electronegativity is closely related to electron affinity, but with a twist.
Okay.
It measures an atom's ability to attract electrons toward itself, but within a bond.
Okay, so it's not just about gaining an electron. It's about how strongly an atom pulls on shared electrons in a molecule.
Precisely. It's like tug of war for those bonding electrons.
And that trend, is it similar?
It is. It also increases across a period and up a group.
So fluorine
The champion.
is the most electronegative element.
It is.
Okay, and noble gases, again, they're not playing this game.
No, they're content.
They're happy with what they have.
They're happy.
All right, so I feel like, we've covered so much already.
Yeah.
But it's not just a bunch of random facts. It's like this beautiful symphony of how atomic structure dictates, an element's properties.
It really is.
And I feel like I'm finally, speaking the language of the periodic table.
I love that.
It's amazing how much information is packed into this one table.
It is, and how these trends, help us understand and predict the behavior of elements.
This has been an incredible journey so far.
I'm glad you think so.
What other fascinating trends are waiting to be uncovered?
Oh, there's so much more.
Okay, I'm ready for more periodic table adventures.
All right.
Before we move on to other trends, our source material mentions something called metallic character.
Oh, yeah.
What exactly does that mean?
That's a great question.
Does it just mean how shiny an element is?
Well, you're not far off, actually.
No.
Metallic character refers to how closely an element exhibits those properties that we think of when we think of metals.
Right.
So like shiny, malleable, meaning you can hammer them into different shapes.
Yeah.
And excellent conductors of heat and electricity.
So like copper wiring or
Yeah.
gold jewelry, those are prime examples.
They are, yeah. And you'll find these metallic elements mostly on the left side. And towards the bottom of the periodic table, generally metallic character increases as you move from right to left, across a period and down a group.
So it's kind of like a diagonal gradient with the most metallic being.
In the bottom left corner.
Like in the bottom left.
Yeah.
Interesting.
So the alkaline metals in group 1 and the alkaline earth metals in group 2, they're like the poster children for metallic character.
Yeah.
They're very reactive. They readily lose electrons to form those positive ions.
Right.
And display all those classic metallic properties that we talked about.
Now, what about nonmetals?
So nonmetals tend to be on the upper right side of the periodic table.
Okay.
Think, oxygen, nitrogen, the halogens that we talked about.
Right.
They're typically dull, brittle, not very good at conducting heat or electricity.
Oh, yeah?
They prefer to gain electrons to form those negative ions, and they're more likely to form covalent bonds.
So is there a clear division on the periodic table between metals and nonmetals?
Not quite. There's a fascinating group of elements called metalloids.
What? Metalloids?
That really blur the lines.
I always thought those were kind of mysterious.
They are.
Where do they hang out on the periodic table?
So they occupy this, diagonal staircase that zigzags between the metals and non-metals.
Okay.
Almost like a demilitarized zone between two superpowers.
I like that. So they have characteristics of both.
They do. Yeah, metalloids are like the chameleons of the periodic table.
They can adapt.
They can adapt. They can exhibit metallic properties in some situations and non-metallic properties in others.
Wow. That's really cool.
It is. And this kind of duality makes them super valuable. Think about silicon.
Right.
Most famous metalloid. It's the heart of computer chips, solar panels.
Right, because it can conduct electricity.
Exactly, but only under specific conditions.
Wow.
Yeah.
Okay, so these metalloids are more than just fence sitters. They are, yeah.
They're important.
They're key players in our technological world.
So how do these like broader classifications of metals, nonmetals, metalloids relate to the trends that we've been discussing?
That's a great question. So for example, remember how we talked about ionization energy? And how it increases as you move from left to right across a period?
Yeah, the closer you get to those halogens, the harder it is to take away an electron.
Well, that trend also reflects the metallic character of those elements.
Okay.
So metals, on the left side, they have lower ionization energies, meaning they lose electrons more easily.
Right.
Nonmetals, on the right side, they have higher ionization energies.
Okay.
Meaning they're more reluctant to give up their electrons.
So is metallic character kind of like an element's willingness to share its electrons?
You could think of it that way. Yeah, metals are the sharers. Nonmetals are much more protective.
Okay, I like that.
Yeah.
So we've talked about atomic radius.
Increasing, down a group and from right to left across a period. But what does this mean in practical terms?
That's a great question. So larger atoms, with their electrons further away from the nucleus, tend to form weaker bonds.
Okay.
Because that attraction between the nucleus and those outer electrons is just weaker.
So a molecule made up of larger atoms would be less stable.
Yeah, more likely to break apart than one made up of smaller atoms.
Right.
That are really holding on tight to each other.
Interesting.
And this difference in bond strength can really influence, the physical properties of a substance.
Right.
So, for example, substances made up of larger atoms might have lower melting and boiling points.
Okay.
Because the forces holding those molecules together are just weaker.
They're just a little bit more laid back.
Exactly.
Interesting. And this applies to, malleability, right?
It does. So metals with larger atoms tend to be more malleable.
Okay.
Because those weaker bonds allow the atoms to kind of slide past each other more easily.
So, gold, which is super malleable, probably has larger atoms than something like iron, which is harder to shape.
Exactly. And this principle also extends to, biological systems.
Oh, wow.
Yeah. The size of an atom can affect how it interacts with enzymes and other molecules in the body. Like certain enzymes have active sites that are specifically shaped to accommodate, molecules of a certain size.
Wow. Okay. So something as simple as atomic radius can have a big effect.
It really can. It's like a chain reaction from the size of an atom to the properties of materials to, the workings of living organisms.
It's all connected?
It is. What about electronegativity?
Okay, yeah. So we talked about electronegativity and how it increases, but how does that translate into real-world things?
So electronegativity is a major player in determining the type of bond that forms between atoms.
Right.
Remember fluorine, the ultimate electron hog? So when an atom like fluorine with very high electronegativity bonds with an atom that has a much lower electronegativity, they form what's called an ionic bond.
Oh, okay. So like sodium chloride.
Perfect example.
Table salt.
Yeah.
Sodium has a low electronegativity. Chlorine has a high one. And so chlorine essentially steals an electron from sodium.
It does.
Creating ions with opposite charges, which are then attracted to each other.
That's exactly what happens. Now, when two atoms with similar electronegativities bond, they tend to share electrons more equally.
Okay.
And that forms what we call a covalent bond.
So like in a water molecule.
Yes.
Where oxygen and hydrogen are sharing.
Exactly. But, oxygen is still a bit of an electron hog.
Right.
It's more electronegative than hydrogen, so it pulls those shared electrons a little closer to itself.
Okay.
But it's not a complete steal, like in an ionic bond.
Right.
This creates what we call a polar covalent bond, where one end of the molecule has a slight negative charge and the other end has a slight positive charge.
Interesting.
Yeah.
So it's like a slightly lopsided tug of war.
Exactly.
And that's what gives water its unique properties.
It is.
Like its ability to dissolve other polar molecules.
It does. And it's also why water molecules are attracted to each other,
right,
forming those hydrogen bonds that give water that high surface tension and make it essential for life.
Okay, so this is how we get from the periodic table to the real world.
Yeah.
This is blowing my mind. I'm starting to see how all of these trends are, the foundation for understanding how the world works on a molecular level.
That's what's so fascinating about chemistry. It's all about understanding those building blocks and how they interact to create, the complexity and diversity we see around us.
Well, I'm definitely feeling more enlightened about the periodic table. I'm ready to tackle more trends.
Okay.
What's next? I'm ready for another round of periodic table discoveries.
All right, let's revisit ionization energy for a moment.
Okay.
Remember how we discussed that it generally increases across a period and up a group?
Yes. And how it's like trying to pry an electron away from an increasingly possessive parent.
Exactly. But we only talked about removing one electron. What happens if we try to remove a second or even a third electron from an atom?
Well, I imagine it gets progressively harder, right?
You're exactly right.
Like trying to take away a second toy from a toddler.
More tears.
Way more tears.
It takes more energy to remove each successive electron from an atom. These are called multiple ionization energies.
Okay.
And they paint a richer picture of an element's electron configuration.
So each electron has its own price tag for removal.
That's a great way to put it.
And the price goes up with each one.
Exactly. And here's the fascinating part. There's usually a dramatic jump in energy when you try to remove an electron from a stable full electron shell.
Oh, that makes sense. Those full shells are like exclusive VIP clubs.
Yeah.
It takes a lot of energy to get past the bouncer.
Exactly. Those core electrons are held much more tightly by the nucleus. It's like trying to extract a deeply embedded splinter.
Ouch.
It takes a lot more effort.
Okay, so the first ionization energy is always the lowest.
It is.
And then it just keeps climbing higher from there.
Yeah, with those dramatic leaps when you try to break into a full shell.
So it's like a fingerprint. Each element has its own pattern.
It is. By analyzing these ionization energy patterns, we can get insights into the arrangement of those electrons within an atom.
Right.
And predict how they will behave.
Very cool. So we're connecting these trends back to real-world things.
We are.
Now, how do periodic trends influence, like, the properties of materials?
Okay, so for example, we know that metals are excellent conductors of electricity.
Yeah.
Why do you think that is?
Well, we talked earlier about how metals really easily lose electrons, forming positive ions. Do those free-floating electrons have something to do with their conductivity?
You got it. In metallic bonding, those valence electrons are delocalized, meaning they're not tied to any specific atom.
Right.
They form what we call a sea of electrons that can flow freely.
Okay, so it's like an electron pool party.
I like that.
And when you apply an electrical current, you're just sending those electrons on a race down the highway.
Exactly. This free flow of electrons is what allows metals to conduct electricity so well.
Okay, so factors like atomic radius and ionization energy all come into play here.
They do, yeah. Larger atoms with their valence electrons further from the nucleus, they tend to lose those electrons more readily.
So they're better conductors.
Exactly.
So elements like cesium and francium must be like superstar conductors.
They are some of the most conductive elements we know of.
Wow.
And this property makes them valuable in a variety of applications.
Like what?
Like photoelectric cells, which convert light into electricity, and atomic clocks.
Wow, so cool. Okay, so these abstract trends really do have real-world applications.
They do.
It's like the periodic table is a blueprint for innovation.
It is. By understanding these trends, we can design new materials with specific properties for different purposes.
So I've gained a new appreciation for the periodic table.
I'm glad to hear that.
It's not just a bunch of squares and letters.
It's a story.
It's the story of the elements and their properties.
It is.
This deep dive has been incredible. I feel like I've unlocked some kind of secret code to understanding chemistry.
I love that analogy.
I know there's always more to learn. What advice would you give to someone who wants to, like, keep exploring this?
I would say, go beyond those basic trends we discussed.
Okay.
Delve into specific properties of different elements, their roles in biological systems, their applications in technology, material science. Uncover the stories behind the elements and how they really contribute to the world around us.
This has been an amazing journey. Thanks for joining us on this deep dive into the periodic table.
My pleasure.
I hope you've come away with a newfound appreciation for this incredible tool.
Me too.
Until next time, keep exploring, keep questioning, and keep diving deeper into the fascinating world of science.